Good afternoon, this is our senior design project. We're Team 6. Our team members are Fernando, Bavuso, Atria, Amjad, Naji, and myself, Gonzalez. We're presenting the compressed air propulsion system. So here's an overview of the main topics that we're going to talk about, such as literature survey and abandoned design concepts. So we wanted to build an eco-friendly compressed air propulsion system that would propel a small boat, and also we wanted to have a universal design that would be adaptable to all type of vehicles. So for our objectives, we have to make a user-friendly compressed air propulsion system that will continuously compress enough air to have a large amount of thrust, and also that will leave no emissions to the environment. So our motivations were to inspire future students to improve in the making propulsion systems in other type of vehicles, also to raise awareness of alternative engines designs, and to reduce the contamination of gases and pollution to the environment. So our goal was to prepare a small prototype boat for the longest time possible, and also to have a low-cost model of this. So when we approached this project, we found that most vehicles in the past that had used this type of systems replaced the use of fuel combustion with compressed air to move pistons. In our case, we'll be compressing air into a tank that will release the necessary air through a nozzle to propel a small boat. For the design of the tank, we found that steel was a good option since it can hold a lot of pressure. Also, we found that a spherical contour for the tank will be ideal since this can hold more internal pressure, but it is very hard to fabricate, and this is why we see most of the tanks made in a cylindrical shape, and that's what we use. Also, we found that even though most of the vehicles that use these type of systems, they do not leave any emissions. They use power plants for the compressor machines, and this contributes in a bigger way to the pollution of the environment. So this is why, to take advantage of the natural resources, we wanted to implement solar panels. We had this in our original design. Unfortunately, for monetary issues, we couldn't afford it to have it in the final design. So this is the most known commercial vehicle in the market. It's called the AirPod. It's a car made by the Motor Development International. It compresses air into a tank at 300 psi to drive pistons, and it creates a power of 35 HP. So we also have some standards. We know that, for example, tanks can be dangerous if they're not properly treated with things such as pressures and temperatures. So we have some regulations from the ISO, and also we have, for example, some guidelines from the IAB to avoid electrical malfunctions into the unit. As we said before, we had some constraints into our project. We didn't have enough time to complete the desired design. We also had some monetary issues. We were not a sponsor, and this led to not having the right equipment to complete the final desired design.
Okay, for the prototype design specifications, what we was do basically is, as an energy source, instead of the solar panels, we implemented a 12-volt deep cycle battery. It was deep cycle because we needed to use it for a long period of time and then recharge it again. Our power compressor is going to compress air into a tank, as Andres said, and then we're going to attach the required thrust mechanism depending on the mission and on the vehicle. For our first alternative design, again, the solar panels, we couldn't afford them, so we moved into the battery. They need to power the motor and an air pump. When you put those two together, basically that's a compressor. Initially we had an aluminum tank, and once the air is fully compressed at the desired pressure inside the tank, we're going to let it out and passing through our nozzle. It's going to increase the velocity of the air, and by exchanging momentum, the boat should propel forwards. For the second design, instead of letting the air go into atmospheric pressure, we decided to inject it into an air turbine, which is going to have a turbine impeller inside, and it's going to be connected to a shaft to a water impeller. This is the casing, the inlet and outlet ports. This is the fully assembly of the components, and the idea is to draw water from the ocean, push it backwards, and same idea. By exchanging momentum, the boat's going to propel forwards. This is the same concept, or similar concept, of the jet skis. And for a third design alternative, instead of attaching a water impeller, the idea was is to attach a huge fan depending on the ratio of the size of the boat, and generate thrust as well and push the back forwards. Another example would be the boats that you can see in the Everglades. For the final design, we chose the first one. It was way simpler. We had to reduce our cost as much as possible. It has a faster assembly. There's nothing really complicated in the prototype. And of course, when I use the nozzle to increase the air velocity, and again, no solar panels were used, just the battery. This is a compressor that we bought. It's a 12-volt compressor. We need a current of 30 amps. These are the inlet and outlet ports of the tank that we use. This valve, the big one right here, is a check valve. It only allows air to flow in one direction, in this case from left to right. At the bottom of it, there's a pin. This pin is very important. It's a safety relief valve, just in case somebody somehow by mistake leaves the compressor on. When the excess pressure inside the tank reaches or passes 120 pounds, the pin is going to open and release the excess air. It is also very important to note that this is a DOT rated tank, so there's no need to concern for safety when testing if treated properly. This is a battery that we bought connected to the clip with the compressor. This is the high pressure hoses connected to a nozzle gun. The high pressure hoses can withstand up to 200 pounds of pressure, which is okay for our design. We had a valve which we used to test the prototype in two settings, which were fully open and half open. This is a nozzle, the nozzle gun connected to the nozzle itself next to a pen, so you guys can have a better understanding of the size and how small the nozzle is. This is the final bolt that we came up with. Again, we use we cannot afford a huge design, so we made a wood platform, 60 by 60, with empty water bottles at the bottom to simulate a catamaran boat. When we actually came to the testing area, we use a pitot tube which it reads the difference in pressures in inches of water. Then we convert it to Pascal, and with that we obtain a velocity. But when we place the pitot tube in front of the tip of the nozzle, the readings were too high and the manometer didn't display any numbers. So we had to improvise, and we came with this idea with a tube. And we expand the air coming into the tube, reducing the velocity, and placing the pitot tube at the other end of the pipe. This is the first person injecting the air into the pipe, and then the other person reading the values on the other side. The principles used apply throughout the project for theoretical and experimental calculations, where the Bernoulli's principle, the continuity equation, the ideal gas, and the momentum equation. For the actual theoretical calculation process, what we did is first, with the ideal gas equation, we calculated the density inside the tank for a certain pressure, and then with the Bernoulli equation, we found the velocity going in the inlet portion of the nozzle, then with the continuity equation, the velocity going out of the nozzle itself, and finally, the momentum.
So these are the values that we obtained for momentum. As you can see, we went from ranges of those pressures that you see there. The above part of the chart are for the valve fully open, and the bottom part of the chart is for the valve half open. We obtained an average of experimental value for fully open of 13 newtons, and half open we obtained an average of 18 newtons. Here's a video of the prototype actually working it. We tested it in a pool. These are some of the prototype specifications. The power consumption of the compressor is 360 watts. The total weight of the prototype is 10 kilograms. And the time it took to fill the tank at 120 psi was 6 minutes, and the time it took to empty is 1 minute. So these are some of the results that we obtained from the testing in the pool. We obtained a distance travel of 20 meters in a time of 38 seconds for an average velocity of 0.53 meters per second. So to scale up our design for a real-life application, what we did is that we applied our concept basically to a kayak, like the one that you see in this picture. So the modifications that had to be made to our propulsion systems were basically, we had to increase the diameter of the inlet and outlet nozzle, as well as the working pressure to 3,000 psi. Some of the specification of the kayak that we use is that we assume a wetted area of 3 meters squared and a coefficient of drag of 0.04. So basically how we set it up is, as I said before, we increase the diameter of the inlet and outlet nozzle, then we increase the pressure as well, we obtain, of course, new velocities. With these new velocities, we were able to obtain the new mass flow rate. Then we multiplied the new mass flow rate by the time we want the system to work, and we obtained the mass moved in kilograms. With this mass in kilograms, we obtained we were able to calculate the volume at ATM by using the ideal gas equation, and then by Boyle's principle, we calculated the amount of volume required at the desired pressure, which in this case is 3,000 psi. Here you can see the system thrust analysis. This is a chart where you can see thrust versus pressure. As you can see from those ranges of pressure of 20 megapascals to 2 megapascals, we can see that we have like more or less an average thrust of 1,500 newtons. So in this next chart, we see the drag force analysis for the kayak. Of course, if we are, let's say for example that we're traveling at 5 meters per second, so the drag force that the kayak creates is about 1,500 newtons. So if we go back to the previous slide, we can see that in the ranges of those pressures from 20 megapascals and 2 megapascals, we actually do have the thrust, so we will be able to be traveling at that desired speed. This is another chart, interesting chart that we came up with. This is for a mission selection. For example, let's say that you want to travel, you want the system to be working for at least 10 minutes. You will require like the volume of the tank to be at least 34 liters, as you can see in the graph.
This table shows the breakdown of our cost analysis components. We'll be able to make our propulsion system cost effective. Therefore, the components were chosen accurately to provide best and excellent endurance and durability. Two of the most components we have in the table, the battery and air compressor. For our design experience and the environmental issues, most of the vehicles there produce emissions. Therefore, our propulsion system should leave no emissions. Our battery, they were fully recyclables to avoid dangers and not to contaminate our environment. And we also need to reduce the use of plastics. For global perspectives, most of the working vehicles out there are propelled through fuel combustions. Therefore, our propulsion system is yet too hard to compete with this ongoing system. For our global design, ideally we would be obtaining power from solar panels, but as my friend Andres expressed, we implemented battery to get power from. We also can have our propulsion system be used all over the world, and we may provide manual in English, Spanish, and Arabic. For our lifelong learning, communication and interaction between our team members have risen the abilities of everyone's skills, and we've also been able to work with different disciplines. Time management is a very important factor. We'll be able to manage our time and arranging every part of the project on a time manner. Looking into different source search has risen the gain of knowledge, knowing about our senior design project. Here we can see our work distribution past semesters, and this finishing up by this semester. And this is our workload distribution among our team members.
Okay, so for future work, ideally we want to build a larger boat hull, even larger than a kayak, to have a real life application. In order to do that, we need to research a little bit more on the direction system. So, for example, if you are going in a kayak, you don't have to steer with your paddle. Instead, you can use, let's say, a hydraulic system depending on the side of the boat. Another good thing that we want to do is implement an air turbine to see the differences between using an impeller inside the water and outside the water. This is due to the fluid densities. And in addition to that, we really want to implement the solar panels because it has a great impact on the environment, which is one of our most important points in the project.
For conclusion, we can conclude that we believe fuel combustions are the easier and ideal way to propel people's working vehicles. Therefore, we believe that our systems, they're not leading the market yet. However, we think that the model will raise awareness for alternative engines. And also, we think that the compressors and power source, it could be an optional debate on both applications, depends on how long we're traveling and how much power we need.
I have a couple questions for you. As far as your design, something that I would have liked to see is, you mentioned you were using a battery or a solar. I think I saw a solar panel somewhere in there. what is going to be the efficiency of that solar panel? How long is it going to take you to charge, whether the battery or power the compressor that is going to fill the tank? That helps you in your scalability slide and feasibility, because if it's going to take you 2 hours to fill a tank to power 1 minute of operation, then you can assume it's not a feasible approach. They could have improvements, but it's not very feasible. The second thing is you mentioned scalability again. On your boat, half of the craft was the vessel or the tank. Does that mean, like, you do calculations on the nozzle, but does that mean now that to reach the same efficiencies of your model, you have to have the tank be half of the kayak now? How does that impact the kayak itself as far as weight? So there's just some work that you might want to identify for future improvements or future analysis that has to be done. I did see on your project that you had some ANSYS work on your tank, but I didn't see it on your presentation. As far as I think you had some pressure analysis or some stress analysis on your tank. Is there a reason you didn't include that here?
We started with the design you can see right there in the board. We tested those, but along the way we saw that manufacturing the tank ourselves was going to be way more expensive. So we decided to buy the tank that was DOT rated, and as you said in the Senior 1 presentation, we didn't want to worry about safety or our safety when taking the prototype.
So the loading pressure that you're using for the tank is the recommended pressure?
Yes.
Okay.
We're not exceeding the pressure because we don't want to damage the plant. In regards with your previous comments, we didn't calculate how much it would take with the solar panels. That's because it all depends on the application, the real application that you want to do. A kayak is something for fun, but it depends on the size of the boat that you want to use. You can apply more solar panels to a bigger boat, and therefore you're going to obtain a larger power. Therefore, you can have a larger compressor to fill it quicker. It all depends on what you want to do with it, and that's why we left it kind of open to play around, to scale it up and down depending on the application that you want to give to a propulsion system.
So first, I would recommend you use weight as you measure that as a traceable property in your design. Seeing that depending on the application, weight might become an impact. You mentioned aircraft at some point.
Yes.
You can't use weight as one of the most crucial measurements. And lastly, could you expand on how you would target the percent error you had on your measurements? Everything was over 50% error on your nozzle measurements.
Yes.
Is there something you would do different?
Yes, we can do, of course, modeling simulations. We have to take into account that the first approach that we use is the Bernoulli's equation, and this is the first point where we start off and we depend everything on it. I believe, we believe that if we take a different approach, a modeling simulation of fluids using ANSYS, it might be the next step to improve the efficiency and to reduce the percentage of error of our design.
So just remember that models take you so far. At some point you have to test to validate your models.
Correct.
So if your measurements already have an error, which I think you attributed to the fact that your pitot measuring device
Yes.
was not registering those measurements.
Correct.
So at this point you can't say my models are correct or they're incorrect because the data shows you different measurements. So that, again, that's something for you to consider. What could you improve in your measurement techniques so that you can come back and say, this is what my model said, this number was going to be 20, and when I tested it, I got 20, 21, somewhere around there. So you can show that your models are valid. And you can use modeling to make changes to your design, and at that point you can say that those changes could be representative without having to retest. Again, just things for you to consider.
How come you didn't bring your model in?
because it was too having too much things. Right? And
Wait a minute, somebody brought a motorcycle in here.
with the video, we thought that you guys can appreciate pictures of every element. So
It's always cool to bring your model in, though.
pictures is better.
That's not as good. Nothing like putting your hands on and seeing what you're actually built. So,
The question I have is around boundaries. Obviously, you can do a motor, you can do a compressor, you can do a tank. Did you ever look at the max battery you can use with the best motor, with the biggest tank? You could run a system like this and look at if it's feasible, how far I can go, for example.
Yes. For that matter, we left that open right here in the conclusion.
I mean, design is open. I understand that, but if you look at the extremes of each end, is there a feasible product in the middle here?
It depends. If you want to go really far, if you want to use the compressor for a long period of time, we thought that it might not be feasible to have the compressor because it would need to be really big, and therefore you're going to need an energy source way bigger than just solar panels.
Okay, so eliminate the compressor.
Yes, and just leave
What
it.
if you just had a tank?
Exactly, that's my
How
point.
big would the tank have
It
to be?
depends on what you want to do and how you want to apply on the boat. At some
Take
point,
the biggest tank you could put on that boat.
it depends
How far
on-
would you
on
go?
On the boat, it depends. And for our prototype, for our calculations, for 10 minutes at 34 liter
Yeah, but 10
tank,
minutes doesn't get me anywhere.
okay, but it's already big.
Yeah,
I mean, for a kayak, the application in a kayak, it wouldn't be, let's say, for transportation. It's just for fun. In case you get tired, that's application that we saw that's feasible for our prototype and our scale up. If you want to go way bigger than that, of course, we think that there's some limitations. That instead of putting a compressor and everything so big, just put an engine. That's
now all of a sudden I have a mission problem.
huh?
So the ecological benefits of this concept no longer
It's
play.
feasible until a certain point. Yeah, it is for in regards of the ecological and environmental issues. Until some point. At some point you have to install an engine.
Okay, thank you.